In section 2, we got error bound for the Lagrange polynomial of degree n, which looks a lot like the Taylor polynomial of degree n error bound, except that it has x minus each of the n plus 1 points in the numerator and the n plus 1 factorial, n plus first derivative, same as Taylor polynomial. But we saw that for some functions, this high degree polynomial, Lagrange polynomial, is very good, very accurate, but for some it's terrible. We saw the example of a Runge function, 1 over 1 plus x squared, which seems to be a perfectly well-behaved function. As n gets larger, the error got really, really large. And well, if you call h the distance between the first and last point, then if you take more and more points, you take n larger and larger, so you're interpolating to more and more uniformly spaced points between the first point and the last point. The total interval is constant h. Then the error is less than h to the n plus 1, because assuming x is between the first and last points, then x minus each of these points is less than the total length of the interval. So each of these is less than h, so that's less than h to the n plus 1 over n plus 1 factorial times the maximum of the n plus first derivative. Well, as n gets larger, no matter how large h is, h to the n plus 1 over n plus 1 factorial goes to 0, so that's not the problem as n goes to infinity. This must be the problem for some functions. For e to the x, it's not, because all the derivatives of e to the x are still just e to the x, but you don't have much control over what the n plus first derivative looks like when n gets large, and apparently for the Runge function it must be huge. So in any case, it's dangerous, and even for a function like e to the x, where it's guaranteed to converge theoretically, the truncation error is guaranteed to go to 0. The round-off error gets huge when n is large, because high-degree polynomials are just very unstable. So high-degree polynomials are basically not good for anything. You never use a 100th-degree polynomial for anything in numerical analysis. So if you want high accuracy, instead of approximating by one high-degree polynomial, you divide your interval into a bunch of small strips of length h and use a moderate degree polynomial in each strip. N equals 3 seems to be popular. Cubic, obviously you can do other moderate values of n, but we're going to concentrate on the case n equals 3 because that seems to be the most popular. So we can approximate the function by polynomials, piecewise polynomials of degree 3. In other words, a different cubic polynomial in each strip. And then as you make h smaller and smaller, you can get more and more accuracy, because that's fixed. N is 3, and that's fourth derivative, maximum fourth derivative is fixed over 4 factorial, but h is going to 0, so this is guaranteed to converge as h goes to 0. So let's look at piecewise cubic polynomial interpolation. And by the way, remember the reason why polynomial approximation or piecewise polynomial approximation is so important is because computers can actually evaluate polynomials, whereas they can't evaluate e to the x or log x or trig functions directly. They have to approximate them by polynomials, and polynomials are easy to take derivatives and integrals. In the next chapter that will be important. Okay, so suppose we've decided we want to use piecewise cubics. You've got choices here. In each strip, you could approximate f by a Taylor polynomial of degree 3, which interpolates to f prime, f double prime, and f triple prime at some point in the interval, let's say the midpoint in each interval. Then the Taylor error formula says the error is less than x minus that midpoint, whatever the interpolation point is, to the 4th power of 4 factorial times 4th derivative. So as the strip size, let's say from xk to xk plus 1, we'll call that h. So we're dividing the whole interval a to b into a bunch of strips of size h. So here's one of them. And in each strip, we approximate f by its Taylor polynomial degree 3 at, say, the midpoint. Then the error is going to be proportional to h to the 4th. But one obvious problem is this piecewise Taylor polynomial is not even continuous. There's no reason why this cubic and the next one are even going to have the same value at where they meet. So the cubic Taylor is accurate, but it's not even continuous. That's not good. Then the most obvious thing would be the piecewise cubic Lagrange, that is, interpolate in each strip of width h by Lagrange polynomial degree 3 that interpolates at 4 points between the first and last point, and then you have a different cubic Lagrange in the next strip and a different one in the next strip. So piecewise cubics, and if you want more accuracy, you just take more and more smaller and smaller strips. And we know the error now is x minus each of the 4 points over 4 factorial times fourth derivative at some point in the interval. And at least L3 is continuous because the cubic Lagrange here and the cubic Lagrange here have the same value here, so they at least meet, but their first derivative is not necessarily continuous. So another option is a cubic Hermite, which is a cubic polynomial. See, all of these are piecewise cubics in each interval. That means they have 4 unknown coefficients in each interval, and you determine those 4 with 4 conditions. The Taylor, you approximate to F 4 times at 1 point. Lagrange, you approximate to F 1 time at 4 points. The cubic Hermite, you approximate F, you interpolate to F and F prime at 2 points, the first and last point in each strip. And so there's your 4 conditions, and that uniquely determines a cubic polynomial that matches F in its first derivative here and F in its first derivative there. And the error bound can be shown to be this. Again, it's proportional to h to the 4th. Anytime you approximate by piecewise cubics, you ought to get order h. Your error should be proportional to h to the 4th. Now h cubed and h cubed prime are continuous because the cubic Hermite over here and the cubic Hermite here have the same value and same first derivative, namely the f of that point and f prime of that point. So they have they're continuous and continuous first derivative, but not continuous second derivative. One problem with the cubic Hermite, though, is that that assumes you know the derivative of f. The Taylor polynomial, that's even worse. You have to know up to the third derivative, but Lagrange polynomial, you don't need to know the derivatives of f. Here you do need to know the first derivative of f, but that's a widely used approximation. But none of those 3 is what we're going to use in this section. We're going to use something different called a piecewise cubic spline, and this is a very popular way to approximate functions for reasons we'll see. And so it's a cubic in each, all 4 of these are cubics in each strip. So you divide the interval a to b into n strips of width h. H doesn't have to be constant, but we'll assume it is. So that length there is h, and there's n strips. And just like the Taylor and the Lagrange and the Hermite, you've got a cubic polynomial in each strip, but this cubic only interpolates to f at the first and last point of each interval. And well, that makes S continuous because it matches f at each point. So this cubic spline and this cubic spline have the same value of S here, so they're automatically continuous. But S prime and S double prime are not necessarily continuous, but you force them to be continuous. In other words, you add conditions and say, I insist that the derivative of this cubic and this cubic be the same, and the second derivative of this cubic and second derivative of that cubic be the same, but not the third derivative. So you've got extra parameters to play with anyway. If your piecewise cubics are only required to match f here and here, then that leaves the cubic underdetermined because there are 4 coefficients of a cubic and only 2 conditions. That there are a lot of piecewise cubics that pass through those 2 points. So you use up your other degrees of freedom by forcing S prime and S double prime to be continuous. So how does that work? Well, if there are a total of n strips, then there are 4 n unknown coefficients, 4 in each strip. and but only two n interpolation conditions. In other words, this cubic has to match the value of F here and here, the next cubic has to match the value of F here and here, so forth. So in each strip you've got two interpolation conditions, so a total of 2n interpolation conditions. But then you say, well, I insist that the first derivative and second derivative be continuous. You don't have to insist that S be continuous, that's already determined. If you enforce that, that'd be redundant. So you only require that S prime and S double prime be continuous because S is already continuous. Well, that's a total of 2 times n minus 1 conditions because there's n minus 1 interior points. See, there's no continuity requirements at the first and last points, only n minus 1 points and 2 conditions of those. So you have 2n interpolation conditions, 2 times n minus 1 continuity conditions, and you add those and you get 4n minus 2. Well, we've got 4n coefficients to determine, so that gives us a system of equations, linear equations of 4n minus 2 equations and 4n unknowns. That's not enough. We normally need the same number of equations as unknowns to have a unique solution, and in fact it will be a unique solution if we get 2 more conditions. So we need 2 additional n conditions. In other words, there are many cubic splines. Everything I've said so far, there's more than one cubic spline that matches F at each of these points and has continuous second, first derivatives. To pin it down, you need extra n conditions, and one possibility is you say, well, let's match the derivative of F at the very first and last point. I mean, we're already matching the value of F, let's match the first derivative. Well, that's one possibility. Or you can match the second derivative at the first and last point. Or another option is just simply set the second derivative of S to 0 at the first and last points. That's called a natural cubic spline, and it sounds like a bad idea. Setting the second derivative of S equal the second derivative of F would surely be more accurate. In fact, it is more accurate if you're trying to approximate F, but there's a good reason for doing this that we'll see in a minute, that this is called a natural cubic spline, where the second derivative at the very first and last point are 0, even if F double prime is not 0 at the first and last point. So in fact, it does make it less accurate if you're trying to approximate a function, but there's a reason for doing this. And one more, the problem with 1 and 2 is that assumes you need to know F prime and F double prime at least at the first and last points, whereas all the other conditions don't, you only need to know F at the other points. So that's the problem with the first 2. And the fourth one is a popular one that simply says, well, make the third derivative continuous at the second and next to last point. So basically this not is not a not, because if the S and S prime and S double prime are already continuous at this point, and you force the third derivative to be continuous, that's all a cubic has, so that means that the cubic here and the cubic next point, next strip are exactly the same, and the same thing with the next to last and last strips. So basically it's an interpolation point, but it's still just a cubic. It's the same cubic in the first and last, so that's called a not condition. And all 4 of these are going to give you order h to the 4th accuracy except for number 3. So what's nice about number 3? Well, before we talk about why a natural cubic spline is popular, how in the world would you find these coefficients? So you've got these 4n unknown coefficients, a plus bx plus cx squared plus dx cubed in each strip. And well, you could just simply, write down all your interpolation conditions and all your continuity conditions and your 2n conditions, and you've got 4n unknowns and 4n equations, and you solve that big system. And notice that unlike the other 3, the cubic Taylor and cubic Lagrange and cubic Hermite, those, if you change F in one strip, you don't change the cubic polynomial anywhere else, only in that strip. So it's like local. You can Taylor or the Lagrange or the Hermite, you can calculate it's here, and then you go to the next strip, calculate it, then next strip, so forth. Spline is different. You have to calculate all the coefficients simultaneously, solving a big linear system. And it looks like you've got to solve a 4n by 4n system. And of course, you're not going to be required to do this, but you could. Turns out that you can actually do the calculations in such a way that all you have to do is solve a tridiagonal system, which is much more efficient. But in any case, you do have to solve a big linear system to find all the coefficients, and you find them all at once. So you change F at one point, that could change the cubic spline everywhere, hopefully not much away from that point. Okay, before we talk more about the natural cubic spline, and you don't worry about how splines are calculated, you're not going to have to calculate them. I'm doing them with a program, MATLAB program, that you don't need to worry about how it works. But recall that in the last video we saw that this Runge function, 1 over 1 plus x squared, if you approximate it using high degree polynomials, you get terrible results. Let's review that. Let's see that again. So if you approximate this Runge function with the polynomial of degree 10 that interpolates at 11 uniformly spaced points, it gives terrible results. And if you try even higher degree polynomial, it gets even worse, much worse. And that's not even round off error. That's actually, that's going to be, no matter how accurate your computer is, it's the algorithm itself. But if you go even higher, 100 degree polynomial, you're going to also have terrible round off error. But so we get bad results here. Let's try now a natural cubic spline. And now we're going to interpolate at 11 uniformly spaced points, but instead of polynomial degree 10, we're going to use a cubic spline which interpolates at these knots. So each cubic in here interpolates to F here and here, and its function and first and second derivative are continuous across the knots, but not the third derivative. If the third derivative were continuous, it'd be exactly the same cubic, so that would be impossible. So you can see this does pretty well, much better than the 10th degree polynomial. Let's go a little higher. And by the way, if I use a not condition or one of the other conditions, it would do equally well. Now let's try 30 uniformly spaced points. It does just fine. The accuracy is 10 to the minus 4, so it seems you can divide the interval into as many strips as you want, and it should get more and more accurate. It's not going to be unstable like the high degree polynomial. On the other hand, for e to the x function, remember Lagrange, a high degree Lagrange polynomial works real well for e to the x. For example, 20th degree polynomial that interpolates to e to the x at 21 uniformly spaced points. The error is really, really small, 10 to the minus 12. It's actually better than the cubic spline. Let's see how the cubic spline with interpolating at 21 uniform, same 21 points. And it does pretty well too, but not nearly as well as the high degree polynomial. However, if you keep making this higher, we saw that the higher and higher degree polynomial eventually goes bad due to round off error. It can't be truncation error, because truncation error is proven to go to 0. And in fact, you have a homework problem where you prove it goes to 0, and we did it in the video. Whereas the spline doesn't go bad. Okay, now let me rerun the cubic spline. And this is natural cubic spline, but it doesn't really make much difference. A little less accurate, but it okay, and what I've done here is I changed one of these points, and we did that same thing with the high degree polynomial. I just arbitrarily moved one of these points up just to see what happens. And with the Lagrange polynomial, that changed the polynomial everywhere, even way out here. With the spline, it does change it everywhere, but less and less the further you get away from it. So this wouldn't happen with the piecewise Taylor or piecewise Lagrange or piecewise Hermite. If you change one point, it's only going to change the piecewise cubic in the two intervals that include that point. It won't change it at all out here because you can calculate them each independently. With the cubic spline, they are, you have to solve a big linear system, so if you change one point, it does change the coefficients everywhere, but doesn't change them way out here very much, so that's good. Okay, this is a page from my computational linear algebra book that we use for 5330, and this is actually the program that I just used to calculate these cubic splines. And as I said, you only have to solve a tridiagonal system, so it's efficient. And the program is here. Well, this is the Fortran version. I have a MATLAB version. You just pass in your data points, and you can, if you set the first and last second derivative to 0, you'll get a natural cubic spline. You see, it isn't really that complicated to program. But now here's the theorem I wanted to look at that explains why natural cubic splines are popular, despite the fact that, if you're actually trying to approximate a function f, it's not going to be as accurate, although the first two options require that you know the derivative or second derivative of f at the first and last points. The natural cubic spline, you just arbitrarily say, I want the second derivative at the very first and very last points to be 0, even if the second derivative of f is not 0. Now, why would you do that? Well, this theorem explains why that's popular. It says, among all functions that are continuous with continuous first and second derivatives, which interpolate the data points xi, yi, the natural cubic spline s minimizes the integral of the second derivative squared. Well, in layman's language, this theorem says that of all smooth functions, of all smooth functions through a set of data points, the natural cubic spline is the least wiggly, because this integral here is like a measure of wiggliness. The second derivative, if the second derivative is 0, that's a straight line. The smaller the second derivative is, the less wiggly it is, the less the curvature is. So this is like a norm of curvature. So it's a measure of wiggliness, which normally you don't want. If you got a set of data points, you want to fit a smooth curve through it. It's kind of a question of opinion. What's the best choice? Depends on what you want, but nearly always you want it to be not wiggly. You want the second derivative to be small. You might say, well, just use a piecewise linear approximation. That'll be the least wiggly of all because the second derivative is 0 everywhere. Well, no, the second derivative is 0 everywhere except at the knots, and then it's infinite. So it's not smooth. So a piecewise linear would minimize this, but it doesn't have continuous first or second derivatives. So you want it to be smooth and not wiggly. And this theorem says in layman's terms that the cubic spline is the least wiggly smooth function, where smoothness defined as continuous and continuous first and second derivative. Wiggliness is defined as the integral of the second derivative squared. So least wiggly smooth function through a set of data points, and that's typically what you want. So in the case where you just have a set of data points and you want to fit a smooth curve through it, and there is no f, you can't talk about the error because you don't have any idea what f is, then this is a good choice. And the proof is kind of interesting, but we won't go through it. So in fact, the word spline, I understand, came from engineers used to take a plexiglass rod and actually nail it to these data points. Let's say you had a set of points, you want a smooth curve through it, you want it to be smooth but not wiggly. Then if you took a plexiglass rod, which you can bend, but it doesn't like to bend. It basically tries to minimize its square, is exactly the second square of the second derivative. That's a measure of the energy, potential energy. It tries to minimize that. So basically it does try to minimize that measure of wiggliness. But you force it to pass through these points, and it's going to be smooth as long as it doesn't break. And so basically if you nail this plexiglass rod, which can bend but doesn't like to bend, through all these points, it will take exactly the form of a natural cubic spline. So you're probably wondering what test and homework problems would look like, since you're not expected to actually calculate cubic spline coefficients. You'd have to solve a big linear system, and just setting it up, even in 2 strips, you've got 8 unknowns and 8 equations, 4 interpolation equations, 2 continuity equations at the midpoint, and 2 end conditions. So 8 equations, 8 unknowns. That would be difficult to solve. So typically test and homework problems are like this. They say this cubic is this between 0 and 1, and it's this between 1 and 2, where A, B, and C are not given, and says what values of A and B will make this a cubic spline. Well, cubic spline means, it's automatically a cubic in both intervals. Cubic spline means that it has to be continuous, and continuous first derivative and continuous second derivative at the point 1, where the two cubics meet. So it's only 2 strips here. They meet at 1, and S prime and S double prime have to be continuous there. You take you set the 2 values, the 2 first derivatives, 2 second derivatives equals each other, and solve for A, B, and C, and that's the answer. Sometimes they'll say, well, it needs to be a natural cubic spline, and then you have the extra condition that at the very first point, which would be 0 in this case, second derivative needs to be 0, and the very last point, second derivative needs to be 0. So that is a typical test or homework problem.